So, welcome to this massive open online course on fluidization engineering. Today will be the lecture 2 on particle properties and classifications. So, in fluidization, particle properties and its classifications play an important role for the behavior and also the performance of the fluidization in a fluidized bed. So, what is these actually particle properties? So, particle properties is an important because you know that the different sizes, shape and strength and true density, particle outline, also Zeta potential acting in such a way that the mobility of the particles inside the bed that will govern the efficiency of the fluidized bed. Also different size of the particles, shape also important for that. So, you will see that these properties like size, shape, strength, porosity, true density and acts the role on flowability, reactivity, caking, even segregation behavior in the fluidized bed. What should be the absorption and adsorption characteristics that depends on the particle properties, what is the caking properties inside the bed and what should be the attrition and permeability. Of course, it is very important for the fluidization. So, we have to know these particle properties before starting the hydrodynamics of the fluidization engineering or in a fluidized bed. Of course, we have to know. And what is the test for particles, so that we can know what should be the size of the shape, what should be the size and shape of the particles and what should be the distribution of the particle and also what should be the particle density, how this particle density will behave, all these things to be known. So, particle size distribution actually being done by sieve analysis or laser light scattering technique. Whereas, particle density, of course, you cannot use bulk density for the specific purposes. Mostly it is being used as a true solid density of the particle for analysis. And also what should be the shape of the particles that can be obtained by microscopic just images. You have to take some images from the by microscope and then analyze its what should be the shape, and also size also you can analyze by taking the image by microscopy, by enlarging or magnifying the images and analysis by some software. And also another important property of the particle, it is called dustiness, will give you the whether these particles will make any dust. That means here if any fine particles are forming, then a dusty formation of course will be there. In that case, because of the ejection velocity, that dustiness will create a problem, and also sometimes clogging and coagulation also possible for a particular fluid velocity by its ejection through the distributor, and all different type of distributor that can be used in the bed. Now, it can be measured in such a way that what should be the gas ejection velocity, depending on the gas velocity, it will be measured or estimated the dustiness. And also other properties like what should be the particle and moisture interactions. Of course, any particle whenever it is being used in a fluidized bed, it will contain some moisture. What will be the equilibrium moisture that contains the particles, and also what will be the other properties of the interaction of the moisture with the particles. You will see some other properties like saturation moisture content, what should be the saturated moisture contained in the particles, and also it should be needed to know because the maximum moisture material can retain without becoming a slurry. So, it is required to know for particular analysis. And also moisture absorption or desorption is very important factor here. You will see powder's tendency to gain or lose moisture at a constant temperature, and it is important to understand caking behavior. And another important factor is dust extinction moisture. So, it is nothing but the material, the material property by which you can say whether this material will emit dust or not. So, moisture at which this moisture does not emit any dust, this is called dust extinction moisture. Another important factor is called transportation moisture limit. Of course, this transportation moisture limit will evaluate the characteristics of the liquefaction behavior of the material. So, these are the important properties for particle moisture interactions to know the characteristics of the particle, and these are like saturation moisture content, moisture absorption or desorption you have to know, dust extinction moisture you have to know, and transportation moisture limit also you have to know. You will see some other properties like particle strength and durability. It depends on particle material, of course, the durability of the particle. Of course, whenever in fluidization operation particles will be used, you will see sometimes the particles will broken down at a high velocity. So, in that case the strength of the particle is important for this purpose. Now, particle breakage force as a function of time required to understand breakage strength of the pellets, okay, whatever it is being used, whether this is this will form any agglomerates or any finished products will be good in nature or not, that also will be depending on the strength of the particles. So, if it is more strength, then of course, it will be the particle breakage will be less. So, here sometimes you will see the finer particles you will see to break it very problem, whereas the hard particle some particles are easily broken down, some particles are not that much extension of durability for its to its original condition. And drop shatter, here measurement of bridge conditioning agents effectiveness on preventing coal caking is very important here. Critical for coal bunker designed for freezing conditions, the drop shatter is very important factor for the fluidization. Now, unconfined compressive strength, this is another important properties of the particle strength. So, you will see the rock breakage strength required for crusher or other comminution equipment selection. So, unconfined compressive strength you have to measure before starting the fluidization operation. Another important, this is very crucial factor, that particle size and the concentration, because you will see the size of the particles will make what should be the flowability of the fluidization. Now, different patterns of the fluidization depends on this size. If there is a smaller or finer or it is a coarser particles, you will see different pattern of the fluidization behavior characteristics, okay, that changes based on the particle size. Sometimes very fine particles is not suitable for fluidization, sometimes some coarser particles are being actually suitable for specific application in the fluidization operation. You cannot use very coarser particles that will be very tough to fluidized also. Also very fine particles also it is not suitable, because it makes some cohesiveness nature or making a clog inside the bed, or you can say agglomeration formation also, it is sometimes possibility there to in the fluidization. So, this particle size and its concentration has direct influence on reactivity or dissolution rate, like catalysts and tablets. In that case, these are used for reactivity or dissolution rate in the fluidization operation. Another important thing is that how you will represent the particle size. There are different ways to represent the particle size, like here sphere of same maximum length, sometimes it is being used to represent the size of the particles. You will see sometimes the minimum particle diameter as a sphere of the same minimum length, it is being represented to show that flow behaviorness in the fluidized bed. And also sphere of same weight. Of course, you will see if you are using the particle of the same weight, and what will be the size, okay, different particles, and if you are using the same weight, then sphere of the equivalent same weight, it will represent what will be the size of the diameter or size of the particle. And also sphere of same volume, it is represented by the same volume of the sphere, if you are representing what will be the equivalent diameter of that particle. Also sphere of same surface area, it is very important. You are just comparing that if different shape of the particles are there, if you are comparing that the surface area, what is the surface area, and if you make it the equivalent spherical surface area, then what should be the size of the bubble that you can represent it. That is represented by ds. Another important sheave, sphere passing the same sheave aperture, what would be the aperture of the sheave, that represented by the particle size also, or this sheave aperture will represent the particle size. Generally, we are measuring in the operation mechanical operation lab how to measure the particle size by the sheave or screen. And however, for irregular shape particles, it is not always appropriate where the size in the where the size in at least one dimension can differ significantly from that of the other dimensions. Here see one figure here, this is one shape of the particle. See here, this is rectangular, this is cylindrical, and this is spherical. So, all these different shape of the particles, you will see you have to make it one equivalent size of the sphere, so that what should be the diameter of the sphere, and if you make the same volume or by same surface or by maximum length or minimum length, or the sphere having the same sedimentation rate, if you are using this type of concept to make the equivalent particle diameter you can have. So, we will show later on that what should be the different definition of the particle, how to measure and how to estimate the different mean of the particle, we will show later on. And then particle size distribution. Of course, for a mixture of the feed, you will see if you solid particle feed is there, you will not get the same all the same size in the mixture. So, there are different sizes of the particles will be in the mixture, maybe within a certain range. Now, what should be that? What should be the number of particles within a certain range of the size? Okay, if you divide into different classes, then you will see there will be a different number of particles will be under in a certain classes. So, if you make it n number of classes, if we make it n number of classes, what will in each classes within a maximum and minimum actually aperture, or you can say diameter range, you will get certain y number or z number of particles will be there. So, for perfectly monodisperse, in that case every single particles has exactly the same dimensions. If you are using, it will consist a statistical distribution of particles of different sizes. It is normal to represent this distribution in the form of sometimes in frequency terms and sometimes in cumulative terms. This is here frequency terms, the x axis it will be in your diameter of the particle, in y axis it will be the RDF. RDF means relative density of the frequency. Here what will be the suppose particle in a particular mean or in a particular class, how many number of particles out of total number of particles, then it is called relative frequency function or relative density frequency function, that is called Okay. So, here in this case you will see the distribution will be like this, and from this distribution you can say in which particle diameter will have the maximum number of particles inside the in the sample. And also cumulative representation of the distribution is important. In this case, in this class what will be the number, it will be just summing up successively, and then it will be represented as cumulative distribution function, and the function will be profile, the functional profile will be like this. And here the, so at a particular particle diameter, what should be the number of particles also you can obtain from the distribution. So, the particle size distributions are classified into weighted distributions, number weighted distributions, volume weighted distributions, and intensity weighted distributions. This intensity weighted distributions means, suppose if you are by analyzing the particle size with its certain color, okay, by a certain color in a image or dynamic way, then how this intensity of the color will change according to its size of this particle, it will give you the some distribution. Volume weighted distribution is also important. What will be the volume of that particular size of the particles will give in a percentage, that is. Number weighted distributions, like what will be the number in a particular class of the particles, that will be given by a distribution. And weighted distributions, of course, it will be what will be the weight, what is the mass percentage of the solid particles in a sample, that will be represented by a distribution. So, this is very important. If you are having all the size are same in the sample, then you will get the only one line distribution of the particles. Whereas, if there is a mixture of different sizes particles, you will get this type of distribution. If suppose this distribution is very narrow, what does it means? This all the particles will be within the very short range of the particle sizes. If it is wider in range, that means here the sample consists the very minimum to the very maximum sizes of the particles in the sample. So, from the distribution you can obtain what will be the particle. This particle size distribution is very important for analysis the hydrodynamics or flow behavior of the particles or any process yield that depends on this particle size distribution. If you are using more finer particles, of course, the surface area of the particles will be more. In that case, the catalyst activity of the fine particles will be more, there may be mass transfer will be more. Whereas, but larger particles or medium sized particles, there if you use, there you will be see some heat transfer operations, mass transfer operations, even some other drying operations also, it will be more favorable. So, you have to know what should be the particle size distribution. Okay. So, this is important for the fluidization operation. If we see this diagram, size distribution variance here increases and here it is size decreasing. What does it means? There are two X scales. If I represent the fluidization characteristics, you will see if we just consider this one, this is low expansion sluggish. What does it mean here? Size of the particles is very high, whereas the size distribution variance will in low. So, in this case the low expansion sluggish inside the bed will be there. That means, sluggish will be more, whereas there will be no expansion of the solid particles is possible inside the fluidized bed. Another important aspect is particle and powder fluidization, where you will see the size distribution. If there is a mixture of different sizes particles, you will see the size distribution will vary. Size distribution will vary. In that case, the wider size distribution may possible, but all the particles are very smaller in range. So, in that case it will exist here, but it may change if you decrease the size. So, in this case, whatever size, if you decrease even more finer particles, as a more finer, you will see more smoother fluidization you can obtain relative to this fluidization in this case. And also here, if you consider these very bigger particles mixed with the finer particles, In this case, the segregation in the fluidized bed will be feasible, and that means easily you can segregate these particles. So, that this distribution will be. In this case, you will see some bigger particles will be and smaller particles. The distribution will be in such a way that you can easily identify these particles, what will be the this particle, what will be this particle, what is the fraction of this particle, what is the fraction of this particle. From the distribution itself you can easily identify. At a different location, if you measure the size distribution, of course, if you take the samples and also analyze, then you will get the size distribution, and from this size distribution you will be able to say, okay, this sample will have more finer particles, or these samples will have more coarser particles. So, in this way you can segregate the solid particles by fluidization by taking its or analyzing its size distribution. Also, you will see if you decrease the size even more, that means here if it is less than suppose 30 micron, what will happen? The cohesiveness of the particles will be there, because intermolecular attraction will be more. In that case, the fluidization is very difficult. So, for finer particles, very finer particles, if you are all the finer particles are the same in size, the particles size distribution will be narrower. So, in that case, for finer particles with narrower distribution, it will be it will not be suitable for fluidization, whereas it can be suitable if you just mix with some other coarser particles. With that, there will be intermolecular attraction will be changed. And also, if you use different size, different nested particle also, like some positive or cationic particles, of course, you will use, you will see sometimes the positive ion particles or ion particles will bind with the negative ion particles, and there it will be fluidizing. So, in that case, some specific example of the fluidization, it may be suitable for having this type of particle size distribution with this cationic and anionic particles also. Sometimes elucidation is very important here, in that case also you have to know how much elucidation is possible from the bigger particles. Or if you initially use all the bigger particles, and after elucidation, after broken down of the particles, and if you analyze that how much solid particles are being broken down, okay, and what will be the size distribution of that, then from these you can at least interpret what should be the elucidation rate, what should be the elucidation efficiency. You can analyze it by the particle size distribution. And for the distribution, of course, you have to analyze something, not only the simple distribution. No, it will not be simple distribution. Here you have to know what should be the mean of that particle size, or average size of the population, that you have to know. What should be the median size, where 50% of the population is below or above, that you have to know. And also another important statistical parameter is called mod, the size with highest frequency. Of course, you have to know, if you are having the highest frequency, that means that particles will be more in number in the sample. And also mean, sometimes this lower range to higher range, if you are making mean, that means if there are different type of means, you will get sometimes arithmetic, sometimes surface mean, sometimes volume mean, volume surface mean. There are different types of means. Definition will be shown later on, but you have to know what should be the mean size of the particles, by which you can analyze the further efficiency or simulation purpose or modeling purpose. You have to know the particular size of the particles. Okay. So, you have to use the mean size of that particles. So, the so this statistical parameter for the size distribution you have to analyze by mean, median and mode. These are the most important statistical parameters. There are some other statistical parameters are there, but these three are being mostly used for fluidization purpose. Now, what is the mean of different particle that is being used for fluidization, that you have to know? What is the definition of the means here? You will see mean diameter you can define in different way. General equation of defining this, it is like dp mn is equal to here summation of ni dpi to the power m divided by summation of this here c in this equation by ni dpi to the power n to the power 1 by m minus n. What is P for particle, D for diameter, and M for these coefficients, N for some other coefficients. So, I 1 to infinity means here here individual particles number 1, number 2, number 3, number 5, now n number of particles will be there. So, if there is n number of particles and if each particle will have its own diameter like dpi, ith number of particles will have the diameter of dp. Okay. So, in that case, if you are defining this dp mean, like here if you are considering that mean diameter, what will be the mean? Arithmetic linear mean. Arithmetic linear mean is defined by m is equal to 1 and n is equal to 0. So, that means here dp 10, dp 10 means here it will be as per this general definition here 1 by n is equal to sum into summation of what is that here summation of I is equal to 1 to n ni dp I. Here this is called arithmetic mean. Similarly, D20, D30, D21, D31, D32, D43, these are the different notation for the definition of the mean of the particles in a sample. So, some are says D10 it is called arithmetic linear mean, D20 it is called surface mean, even D21 it is called surface diameter mean, even D32 it is called outer mean, even D43 it is called de Broca mean, and also D30 is called volume mean. And this arithmetic mean here, the respective definition is given in the slides. Okay. So, how it will be defined, and also all this mean diameter actually for analysis for different processes are being used specifically, like arithmetic linear mean generally is used for evaporation purpose, and D20 that means surface mean it is being used for absorption, D30 that is volume mean it is being used for any hydrology processes, and also surface diameter mean like adsorption, even volume diameter mean it is D31 it is generally being used for analysis of evaporation or molecular diffusion with the samples, and Sauter mean it is very widely used mean for the samples of different sizes particles. This is for efficiency studies of like mass transfer, gas liquid reaction, even gas liquid solid reactions in the fluidized bed. This particle mean are being represented by this Sauter mean. This is D32, that means here volume to surface mean diameter. D43 de Broca, this is also one important for fluidization. This is for combustion. If you are using combustion in a fluidized bed, what should be the equivalent particle diameter is being there produced, then you can analyze by this D43. D43 here that means here m is for 4 and n for 3, here 3 for volume, 4 for even surface square, that means here this is defined in this way. So, combustion, equilibrium and spray system, these means are very widely used. Okay. So, these are the different definitions of the means you can use for different purposes in the whenever you are using in fluidized bed, that is D32, D43 and this is D30. These threes are very widely used, even it is suggested to use for different operations. Now, another important to analyze that particle size distribution by percentiles. For volume weighted particle size distribution, you will see such as those measured by laser diffraction, it is often actually convenient to report parameters based upon the maximum particle size for a given percentage volume of the sample. Here suppose you see particle size and this is volume percent, this particle size D50 or D10 or D90, this nothing but 50%, D50 here means 50% of the particles are volume percent is like this, and also here d90 90% of the particles are size in d90 like this micrometer. So, percentiles are defined as x alpha b here. Alpha this x alpha beta, where x is the parameter, usually this is being used for diameter, d for diameter, and alpha is the distribution weighting, example suppose n for number here, and v for volume, I for intensity, and beta is the percentage of sample below this particle size, example like 50% sometimes written as a decimal fraction, that is 0.5. So, here very important, the sample below this particle size, example 50% of this, that means here within this diameter of the particles like x alpha b here, in this case these particles represent the 50% of the volume of the particles will be diameter less than this particle size. And here 90% of the, in this case this 90% of the particles in the samples will have the diameter of the particles less than this d90. Okay. Similarly, the most common percentiles reported are dV 10, dV 50 and dV 90 as illustrated in the frequency and cumulative plots in the figure like this. Here within this is the 80% of the samples will have the particle size and frequency overall of the total volume. This 80% of the volume will contain the number concentration of the particles, 80% of number concentration will be within this region of 10% to here 10%. So, this is the representation of the percentiles in the particle size distribution. This is also one important, sometimes if you are going to analyze the particle size by what is that laser diffraction method, like Mellon particle size analyzer, there also it is being analyzed by what is the volume percent, what is the number percentage. You can convert it from volume percentage to number percent to volume percent if you know the particle size also. And within a certain range of the particle, what the percentage of the solid particles will be in the distribution, that you can read from the distribution of the parameter. Okay. And then this particle shape, this is also important. All the particles you will not get the same in size. Of course, some particles will be more in diameter, even some particles will be rectangular, some particles will be cylindrical, some particles will be only just rod like, some particles will be even irregular in shape. So, this shape of the particles also very important to analyze the fluidization behavior in the fluidized bed. Now, in that case, how this particle shape will also will affect on the flow behavior in the fluidized bed or performance of the fluidized bed, like reactivity and solubility, like pharmaceutical actives. In that case also it may vary the reactivity because of the size of the particles. Sometimes uniform particle size will mostly actually favorable for uniform mixing and also yield of the processes. And also ceramic sinter property is important. In that case, if you use different shape of particles, this sinter properties of course will change. And also powder flow and handling, you cannot have the same flowability with the different shape of the particles. Even you will see texture and feel. If you use the different shape of the particles, the texture of the particles in the food as a food ingredient will vary. So, particle shape parameters sometimes in the 2D projections you can measure by the aspect ratio. This aspect ratio is nothing but what will be the width of the particle and what will be the length of the particle, by which you can represent the particle shape, or you can say the particle shape, you can say the particle shape parameter by which you can analyze the flow behavior inside the fluidized bed. And then particle outline. The outline of the particle, it will provide the information about properties such as surface roughness. For conducting particle outline parameters, a concept known as convex hull perimeter is used. Convex hull perimeter you have, if you know, then by this convex convex hull perimeter will give you the outline parameter of the particles. Here see on the determining the convex hull perimeter, some parameters based on it can be defined such as convexity or solidity, where this convexity is defined as what will be the ratio of convex hull perimeter and actual perimeter. Suppose this is the irregular shape particles here, what would be the perimeter? Perimeter, just considering the what is that the peaks of this hull of this objects. So, just joining this point of this peak of this different actually point of this particles, and what should be the perimeter, this is called convex hull perimeter, whereas actual perimeter will be, if you just go through this like this exactly, wherever is there curvature, if you consider the length of that due to that curvature, this will be the actual perimeter. So, if you divide this convex hull perimeter by actual perimeter of the object, then you will get the convexity. So, this convexity is the one parameter of particle outline to represent. Another important is solidity. Solidity that is defined by area bounded by actual perimeter by area bounded by convex hull perimeter. So, in this case what would be the actual perimeter, of course, you can obtain and from which you can calculate what would be the area covered by this perimeter, and also what should be the area bounded by convex hull perimeter. So, those things are not same actually. So, there will be area difference. So, what should be the area of this convex hull perimeter and area of the actual perimeter? If you just make it ratio, you will get the solidity. So, this solidity of course will be is less than of course 1, because this area bounded by the convex hull maybe is greater than the area bounded by the actual perimeter. Circularity is also one important parameter used for particle characteristics. The circularity depends on the, of course, that what will be the actual perimeter and what will be the perimeter of an equivalent area circle. So, if you are having this is, suppose this is one object and this the what will be the actual perimeter, and if you consider that this perimeter has a perimeter of circle, then what should be the area of that circle, just making it as what is that pi r is equal to this perimeter, 2 pi r is equal to this perimeter, and what is that area is pi r square. So, what would be the r of that? So, you can calculate the circularity from this portion. Now, another important is Zeta potential. It is generally being used your liquid solid operations in fluidized bed or in gas liquid solid operation in fluidized bed. Zeta potential, it is actually it will measure the magnitude of the electrostatic or charge, whether it is repulsive or attractive, how much charge is there for repulsion and attraction between particles, okay, in a liquid suspension. So, Zeta potential will give you its measurement. Okay. Now, that means here this Zeta potential will give you the what should be the magnitude or degree of the electrostatic charge, which is being actually for repulsion or attraction between the particles. And this is of course important, because sometimes the stability of the solid particles inside the bed for liquid solid or solid liquid gas operation, it is very important, because you have to anyway stabilize the system in a fluidized bed for stability, for better dispersion or you can say uniform dispersion with stability, you have to know this Zeta potential. and whether these particles will attract some other particles or not, it will make coagulation, or it will make any what is that bigger particles by conjugating with the negative charge particles or other charge particles. That depends on the zeta potential. Can be applied to improve the formulation of dispersion, emulsion and suspension. Of course, if you know the zeta potential, you will be able to know how much dispersion will be there, how much emulsion, what is the characteristics of the emulsions, what is the emulsified, what extent of this emulsification is possible, and also is it making any the stable suspension or not. You can interpret by the zeta potential. Now, what is that zeta potential? How to estimate that zeta potential? This zeta potential here, Smolowski's equation is important here. That case, zeta potential is defined as mu e eta divided by epsilon r into epsilon 0. What is mu e? Mu e is nothing but mobility. Mobility. This mobility means here, this whenever solid particles are kept in a solution, whatever these solid particles will try to move aside by attraction or repulsion of the relatively with other particles also. So, in that case, if you are making it free, okay, there will be no mobility. If only due to the settling velocity will move down, but if there is different sizes particles, different charged particles, if you put into the sample, what will happen? One particle will attract another, another particle should repulse another particles. So, in that way the mobility will change because of this nature of the ion of the particles. So, this mobility you have to measure, and then what will be the extent of that mobility, that can be measured by the instruments. Specific instruments are being used. It is called zeta sizer, or there are several equipment. That is a standard method to measure this mobility. And also what will be the viscosity, that is eta. Eta is called dynamic viscosity of the dispersion medium in which the solid particles are dispersed. And Xi is zeta potential, and epsilon r and epsilon 0. Epsilon r is the dielectric constant of the dispersion medium, and epsilon 0 is the permeability of the free space. So, these parameters will give you the what will be the zeta potential. You will see there is some ranges of the zeta potential, and what will be the effect of this range of zeta potential on the stability behavior of the colloid medium inside the bed. So, from 0 to plus minus 5, it may be plus, it may be minus, of course, based on the ion of the particles and also mobility. So, in this case 0 to plus minus 5, it will give you the rapid coagulation or flocculation. From plus minus 10 to plus minus 30, you will see incipient instability, and from plus minus 30 to plus minus 40, it will give you moderate stability. From plus minus 40 to plus minus 60, it will give you good stability. For more than 60, plus minus 60, it will give you the excellent stability. So, if you are getting more excellent stability, you have to use the particles in such a way that the zeta potential will be more than 60. Okay. So, these are the here in picture, there are different particles, of course, having different charges, some positive, some negative, and whenever you are using one surface charge is making, and surrounding this there will be a positive ion, and even another layer, if you are putting that, some other negative ion will come to this positive ion particles, and there will be attraction. So, there are different layer by making a population of the different ions, and from which you can obtain the mobility or potential of the particles just from one point to another point, and from which you can be able to measure or estimate the zeta potential. Now, important classification of the particles. Now, whatever particles are you are using, that is very important, how it can be classified, of course, you have to know the in fluidization purpose whether this classification of the particles, whether it is the smaller particles or finer particles, or you can say coarser particles, that. Okay. So, 1973 Geldart he has given the standard segregation or standard way of representation of the particle by classifying a different group, and he actually categorized the particles based on the diameter and the relative density of the particles, relative density of the particles to represent that different groups of particles, and segregate that in different groups based on their size. And he actually identified 4 regions in which the fluidization character can be distinctly defined. What are those 4 regions of the particle class? He has defined the 4 regions like C, A, B, D. What is this C? C means cohesive group. That means here the solid particles size will be ranged between 0 to 30. That means up to 30 micrometer you can define this particle as a cohesive nature particles. This is very fine particles, and because of these fine particles, this you know that van der Waals force or this attractive force will be more higher, and because of which you will see that cohesiveness nature will exist in this group. So, that is why this is categorized as C group. C means cohesive. Example like fluor particles, whatever in market commercially available, you will see the particles are very fine. It will be less than 30 micron in size, because this, and also you will see whenever you will add some water in the particles, that the particles will, you will see very difficult to segregate from each other. So, that is why it is called more cohesiveness in nature. And here in this case this attraction between the particles will be very high. And another type is called aeratable. Aeratable means here in this case you will see, if you allow some gas through this space of these particles, you will see the gas will be escaping from its space between the particles. So, this aeration possible by these particles. In this case, the size of the particles will be within the range of 30 to 100 micrometer. So, like milk powder, you can easily flow, you can easily fluidize this milk powder, okay, but just by aeration. So, this is called, why it is called aeratable. In this case, size will be within the range of 30 to 100 micrometer, and generally low particle density are being categorized in this case to 1.5 gram per cc. Another one is bubbling. I think I have shown that that bubbling fluidization. So, bubbling fluidization occurs on the B type particle. This B type particle means the size range will be 100 to 1000 micrometer. Like sand, if you are using sand particle within the range of 100 to 1000 micrometer, you will see the formation of bubble inside the bed. So, in this case the attraction force will be not as much higher than the C type particles or B type particles. Another type, it is called D type. In this case the particle size will be very coarser, that means the size range will be greater than 1000 micrometer. Like coffee beans, the size is greater than 1000 micrometer. So, in this case the spoutable nature of the fluidization occurs. You will see the gas will be making a channel through the space of the particles, and also there will be certain thrust of the gas particles, and also movement of the solid particles downward and upward, and in a certain fashion the gas will be moving up. So, in that case the this is represented by this spoutable type of diameter or spoutable type of particles like coffee beans. The drying grains or peas, roasting of coffee beans, you will see the gasifying coals also, this type of particles are being used for that operation, and it is feasible. Effect of particles on the fluidization quality, how this particle size based on these forces will affect the fluidization quality. And if you see this, if you decrease the particle size and if you increase the particle size, in this case the agglomeration behavior will increase because of this change of the particle size. If you decrease the particle size, agglomeration will decrease, whereas if you increase the particle size, this individual particle behavior will increase. Okay. So, points. So, this is actually basically that how this force will be applied in the fluidization quality, and also the size it matters, and what should be the different sizes. So, these are the things, basic things that you have to know, what will be the particle size, how it will behave on the fluidization. Okay. So, next class we will discuss the Geldert different classification of the particles of powders, and others this size of these particles or classified size of these particles, how it will change the flow pattern of the fluidization. Thank you.